continuous time Markov chain, Sidney Chapman and Andrei Kolmogorov. These are two great mathematicians who have contributed to Markov chains. Sidney Chapman is a British mathematician and Kolmogorov, we know that he was a famous Russian mathematician. We discussed discrete time Markov chain where both state space and the time is discrete. Earlier we discussed DTMC. So we will discuss now CTMC, continuous time Markov chain, where time is continuous. Time is continuous and state space V is discrete. Okay. And continuous time Markov chain has many applications. For example, that queuing system, population studies, etc., where CTMC, different type of CTMC gets applications. We will start with the definition of continuous time Markov chain. Consider a random process xt, t greater than equal to 0, where state space V is either finite or countable. Basically, it is discrete. Xt is called a continuous time Markov chain if given time instances t1 less than t2, like that tn less than s plus t. So we have different instances of time starting with t1 to s, then s plus t, and integers I1, I2 up to in, then ij. These are the state values actually belonging to V. We have now what is the condition for CTMC, same as a definition of Markov process, that is probability of x of s plus t is equal to j, given that xs is equal to I and remaining instances x of tk is equal to ik, k is equal to 1, 2 up to n. So, this is the conditional probability we want to find out. This is same as probability of x s plus t is equal to j, given that xs is equal to I. So, the conditional probability given that all the previous instances depends only on the current instance. So, that way probability of x s plus t is equal to j, given that xs is equal to I. Now, this probability is important for continuous time Markov chain, and this is called this transition probability, state transition probability. Pij we can write pi comma j or pij for simplicity. Pij st is equal to probability that x of s plus t is equal to j, given that xs is equal to I is the transition probability. Now we will discuss about homogeneous CTMC. Suppose Pij st is independent of s but dependent on t. We call the chain to be homogeneous. In that situation, we call the chain to be homogeneous. So, that means Pij st is a function of t but not a function of s. If xt t greater than 0 is a homogeneous CTMC, then Pij t is equal to probability of x of s plus t is equal to j, given that xs is equal to I, is same as, now because it is homogeneous. So, what we will get is probability of xt is equal to j, given that x0 is equal to I. So, that is one important relationship, because it is independent of starting point s. So, we can write it as Pij is equal to probability of xt is equal to j, given that x0 is equal to I. Now, suppose we have to find out any state probability, suppose Pj, that is the probability of state j at instant t. So, probability of xt is equal to j. So, how we can find it? Summation over I pi0 into Pij t, because this will give the joint probability and from that joint probability, if we sum over I, then we will get the marginal probability. So, that way we can find out PJT. So, PJT is equal to that is first joint probability Pi 0 into Pij t and summation over all I. So, this is the state probability at time t. We will see the transition probability for independent increment process. So, Pij st is equal to probability of xt plus is equal to j, given that xs is equal to I. So, that by definition of conditional probability, probability of x of t plus s is equal to j and xs is equal to I divided by probability of xs equal to I. Now, this joint probability now can be written as probability of xs is equal to I probability into probability of x of t plus s minus xs is equal to j minus I, given that x of s is equal to I, but because of the independent increment property, we write simply probability of x of t plus s minus xs is equal to j minus I. So, this and this get cancelled. What we will get is that Pij st is equal to probability of the increment, probability of x of t plus s minus xs is equal to j minus I. That is the transition probability in the case of independent increment process. We want to study the behavior of the continuous time Markov chain. So, for that, state holding time is an important concept. When the CTMC enters a state I, the time it spends there before it leaves is called the state holding time. So, for a CTMC, suppose it will enter a state I and it will remain in the state I for some random time Ti, that time is known as the state holding time, and it is a continuous random variable because Ti can be any time. Now, we have one important theorem which has two parts. Part A says that Ti is memoryless. What does it mean? That probability that Ti greater than t plus s, given that Ti greater than s is same as probability of Ti greater than t. So, probability of Ti is greater than t plus s, but given that Ti is greater than s. So, this probability, conditional probability, is same as unconditional probability that Ti is greater than t. So, that way that it is already Ti is greater than s, that does not have any implication on Ti greater than t plus s. So, this is the memoryless property. And second thing is that Ti is exponentially distributed with parameter nu I, where nu I greater than 0 is a constant. We will prove both parts. First, proof of first part A, probability of Ti greater than s plus t, given that Ti greater than s. What does it mean? Probability that xu is equal to I up to during the interval 0 to s plus t, because there is no change in state. Given that xu is equal to I during the time 0 to s, given that there is no change in state during time 0 to s, the probability that there will be no change in state during time 0 to s plus t. Now, this probability, because here u lies between 0 and s plus t and here u lies between 0 and s. So, this probability will be same as already given that xu is equal to I for u lying between 0 and s. Therefore, this probability will be same as probability of xu is equal to I, u lies between s and s plus t, given that xu is equal to I for u lying between 0 and s. Now, we can use the Markov property. So, that way we will get probability of xu is equal to I, u lies between s and s plus t, given that xs is equal to I. So, this we get using Markov property. Okay. So, then what we will get is that probability of x u is equal to I. Now, because of the homogeneity property, we can consider u lies between 0 and t, given that x 0 is equal to I. So, this is same as probability of t I greater than t. So, that way we have used the Markov property once, then we use the homogeneity property and prove that probability of t I greater than s plus t, given that t I greater than s is same as probability of t I greater than t. Thus, t I is memoryless. We will now prove part B. Now, let us consider the probability that t I is greater than t plus s, and that is, suppose this is the time axis, this is the point t plus s, and this is the point, suppose s. Now, probability that t I greater than t plus s, now t I greater than t plus s, this side is t I greater than t plus s. So, this right hand side interval is, this interval is t I greater than t plus s. Now, this interval if I consider, that is t I greater than s. So, you observe that t I greater than t plus s is the intersection of two intervals t I greater than s and t I greater than t plus s. So, that is why probability of t I greater than t plus s is same as probability that t I greater than t plus s intersection t I greater than s. So, now we can write, suppose if we take this as the first probability, that is probability of t I greater than s into probability of t I greater than t plus s, given that t I is greater than s. Now, using the memoryless property, so this probability will be same as probability of t I greater than t. Therefore, what we get is that probability of t I greater than t plus s in the case of this state holding time is same as probability of t I greater than s multiplied by probability of t I greater than t. So, this quantity is the complementary CDF. Therefore, in terms of, because we know that suppose f(x) of x is probability that x less than equal to small x. Therefore, complementary CDF f(x) cx complementary CDF is equal to 1 minus f(x) of x, that is equal to probability that x is greater than small x. So, this is the definition of complementary CDF, and therefore, in terms of complementary CDF we get that FTIC at point s plus t is equal to FTIC at point s into FTIC at point t. So, complementary CDF at point s plus t is the product of complementary CDF at instant s into complementary CDF at instant t. Taking the logarithm both sides, we will get that log FTIC s plus t with base e is same as log of FTIC s base e plus log of FTIC t base e. So, this is the remarkable result, that is the logarithm of a function at the sum of the two arguments is same as logarithm of the function of at one argument plus logarithm of the function at the other argument. So, logarithm of the sum is equal to sum of the individual logarithm. The only function that satisfies this relationship for arbitrary t and s is, that is log of FTICT must be equal to minus nu y into t, where nu y is a positive number. So, that what we will get, FTICT is equal to e to the power nu I t, and this is equal to 1 minus FTIT, and therefore, if we take the derivative, this quantity is 1 minus f ti t is equal to e to the power minus nu I t for t greater than 0, greater than equal to 0. Now taking the derivative, with respect to t, we get what we get, what we will get, derivative of this is 0, derivative of this is the PDF, and right hand side similarly we can take the derivative and we will get f ti of t is equal to nu I into e to the power minus nu I t, t greater than equal to 0. So, this is the PDF of the state holding time. So, that way we have established that state holding time is memoryless and it is distributed as the exponential random variable. After defining the state holding time, we can get the structure of a homogeneous CTMC. The operation of a CTMC is as follows. Once CTMC enters at state I, it stays at the state for a time ti which is exponentially distributed. That we have established that it will remain in state I for a random time with PDF exponential nu I. Once the CTMC leaves state I, it enters one of the state j with the transition probability Pij, j not equal to I, such that summation Pij is equal to 1. Suppose it is in state I. Now, after leaving the state I, it will go into other states, but not this state. So, that way it will, suppose there is a state j, so it will go to state j with probability Pij, such that sum of all these probabilities where j not equal to I must be equal to 1. So, after leaving the state I, it has to go to one of the states j with probability Pij, such that summation of Pij is equal to 1. Also, due to events of leaving the state I and entering the state j are independent because of the Markovian assumption. Now, this process of jumping to state j from state I is like a discrete time Markov chain and is sometimes called an embedded Markov chain. So, along with a continuous time Markov chain, there is always an embedded Markov chain, and the structure of the embedded Markov chain determines the nature of the CTMC. The structure of this embedded Markov chain determines the class property of a CTMC. Example, Poisson process. Suppose the Poisson process has entered state I at time 0. It will remain in same state until the next arrival, which is exponentially distributed. Once an arrival takes place, the number of count in the Poisson process will go up by 1, that is, this state will become I plus 1. Therefore, for j not equal to I, Pij will be always equal to 1, for j is equal to I plus 1 is equal to 0 otherwise. So, once it leaves state I, it will go into state I plus 1 with probability 1 and remaining state with probability 0. Let us see the short time behavior of the chain at a time interval t plus delta t. This behavior will determine the dynamics of the CTMC, so that we can get the corresponding equations which govern the behavior of the CTMC. Now, Pii delta t, that is the probability that state holding time Ti is greater than delta t, and that means there is no transition during the time t and t plus delta t. Plus O delta t, suppose this will take account of if there is multiple transition from state I, it has go to state j, and it has again come back to state I. So that probability will be less, so that we have denoted by O delta t. And therefore, this time we know e to the power nu I delta t plus O delta t. And if I expand e to the power nu I delta t, then I can write it as 1 minus nu I delta t plus remaining term I will club with this O delta t, it will be O delta t only. So this is the probability that the state will be I after delta t, given that it is at state I at time instant 0. So that way we can interpret this probability. So from this what we will get? 1 minus pii delta t, 1 minus pii delta t, 1 minus pii delta t divided by delta t is equal to nu I. That is one important result. Now let us see what happened for j not equal to I. In that case pij delta t. So what will happen? That random time is less than delta t, state holding time is less than delta t, that is the probability that ti is less than delta t, multiplied by now there will be a transition from state I to state j. So multiplied by pij, this is also capital P. So this will be equal to again 1 minus e to the power minus nu I delta t, that is the probability that ti greater than less than delta t. So greater than delta t is e to the power nu I delta t, that we have derived. So that way less will be 1 minus e to the power minus nu I delta t multiplied by pij. And this quantity again if I expand in terms of that is exponential series, the e to the power minus x, suppose if I expand, then I will get this term 1 minus e to the power minus nu I delta t is nu I delta t plus O delta t and whole multiplied by pij. So that way we will get nu I delta t multiplied by pij plus O delta t. Now this quantity, actually this nu I into pij delta t plus O delta t. Now this quantity nu I into pij, that is known as the probability rate function. So and we denote it by qij. So that way qij into delta t, that will become probability. So qij is a probability rate function. Now let us see the sum of the this qij values. Sum of qij, j not equal to I, because there will be no transition to state itself. So that way this is j not equal to I, that is equal to nu I into pij, summation over j not equal to I is equal to, that will be, now this I know this quantity is equal to 1. So this will be equal to, therefore this will be equal to nu I, because this quantity is equal to 1. Now if I denote that nu I is equal to minus qii, because here I do not consider qii and sum of this quantity is nu I, therefore if I denote qii is equal to minus nu I, then I will get summation of qij over all j is equal to 0. Here we got the summation of qij, j not equal to I, that is equal to nu I. Therefore if I let qii is equal to minus nu I, then I will get this sum is equal to 0. So that way this sum of the probability rate function qij over all state, if I consider, that must be equal to 0. On the basis of the above discussion, we present two important lemmas about the short term behavior of continuous time Markov chain. Lemma 1 states that limit 1 minus pij delta t divided by delta t as delta t tends to 0 is equal to nu I. So 1 minus pii delta t is the probability that the chain leaves state I during delta t. So this is 1 minus pii delta t. Now according to this lemma, therefore the rate of the probability of leaving the state I is equal to nu I. Similarly, lemma 2 states that limit Pij delta t divided by delta t as delta t tends to 0 is equal to Qij, where Qij is equal to nu I into Pij. So this Pij is the state transition probability of the embedded Markov chain. So according to this lemma, the rate of the probability of entering the state j from state I is equal to Qij. So these two lemmas will be very useful in deriving the differential equations governing the evolution of continuous time Markov chains. Kolmogorov equations for a CTMC. We know this Chapman-Kolmogorov equation, that is Pij s plus t, that is very obvious. We can write it as summation over Pik s over k into Pkj t. So Pij s plus t we can write as summation Pik s into Pkj t over k. So this is the Chapman-Kolmogorov equation. So first we consider transition to state S, and from state S to Kolmogorov equation for CTMC. We can get this Chapman-Kolmogorov equation for continuous time Markov chain, that is Pij s plus t is same as summation Pik s into Pkj t. So this is the transition to state k during S, and from state k to state j during t. So that way we can get the Chapman-Kolmogorov equation. But for describing the chain dynamically, Kolmogorov forward and backward differential equations are used. First we will derive the Kolmogorov backward differential equation. So here what we assume is that suppose to reach state j at t plus delta t, there is transition from state I to some state during delta t, and then from those states there will be transition during t. So first this is the time instant delta t we consider, and remaining time we will consider later. So that way it is backward, delta t is before t plus delta t. So that way backward thing will come. Now Pij t plus delta t, that is equal to probability that x of t plus delta t is equal to j, given that x0 is equal to I. So Pij at t plus delta t we are interested to find, then we can find out the derivative. So this is same as, so from 0 to delta t we can consider, and from delta t to t. So that way this is same as summation Pik delta t into Pk j t summation over k. Now here we can separate out Pii delta t into Pij t. First term we have taken out, k is equal to I term we have taken out, and remaining term suppose k not equal to I. So this will be summation Pik delta t into Pkj t. Now I know that Pii delta t is equal to 1 minus nu I delta t plus O delta t into Pij t, plus remaining term. Now I know that Pik delta t using the lemma 2, that is equal to Qik into delta t multiplied by Pkj t. So that way we have Pij t plus delta t given by this expression. Now if I take this Pij t to the left hand side and divided by delta t, and consider when delta t tends to 0, then we will get this limit is equal to minus nu I Pij t, because this delta t will come here to the denominator. So, that way minus nu I into Pij t plus Qik into Pkj t, because delta t will come to this denominator, and as delta t tends to 0, this will be the derivative of Pij t. So, Pij dash t will be equal to nu I Pij t plus Qik Pkj t k not equal to I. So, this is the Kolmogorov backward equation. Similarly, in the forward equation, we consider first time t 0 to t, then t to t plus delta t. So, here Pij t plus delta t will be Pik t, because there will be transition to state k during time t, Pik t into Kj delta t. So, we can consider here one k is j. So, that will be Pij t into Pjj delta t plus summation Pik t into Pkj delta t, where k not equal to j. Now, this quantity I know, and this quantity also I know. So, that way using lemma 1 and lemma 2, I can write this as this quantity as 1 minus nu j delta t plus O delta t multiplied by Pij t. So, this term I am writing using lemma 1. Similarly, in the here also I use the lemma 2 to get this term Pkj delta t is equal to Qik Qkj delta t Pkj delta t is equal to Qkj delta t plus O delta t. So, that we have written using lemma 2. So, now what we will do is we will take Pij t left hand side and 1 into Pij t, that is equal to Pij t. So, this we will take to the left hand side and divided by delta t. So, what we will be left with, as delta t tends to 0, what we will get is that Pij dash t, that is the derivative, is equal to minus nu j into Pij t plus summation Pik t Qkj k not equal to j. So, this is the forward Kolmogorov equation, and we can also earlier define that Qjj is equal to minus nu j. Then we can write this term also, we can club along with this summation. We can write Pij dash t is equal to summation Pik t into Qkj over k. This is the Kolmogorov forward equation, because here that incremental part we have considered after t. So, that way it is forward equation. Earlier we derived the backward equation. Let us summarize the lecture. When a CTMC enters a state I, it spends a random duration Ti. This is the state holding time, and Ti is distributed as exponential distribution, that is Fti of t is equal to nu I into e to the power minus nu I t, where nu I is greater than 0. Once the CTMC leaves state I, it enters one of the state j with the transition probability Pij, where j not equal to I, such that summation Pij over j not equal to I is equal to 1. So, once the CTMC leaves the state I, it will enter into one of the state j with probability Pij. We also stated two important lemmas regarding the short term behavior of a Markov chain. These two lemmas are lemma 1, this was the lemma 1, limit 1 minus Pii delta t by delta t as delta t tends to 0 is equal to nu I, and lemma 2 was limit Pij delta t by delta t as delta t tends to 0 is equal to Qij. Now, to characterize the transition probabilities dynamically, Kolmogorov backward and forward differential equations are used. So, what we got? Kolmogorov backward equation, that is Pij dash t is equal to summation over k qik. So, initially in delta interval of time it will go to state in state k. So, that is taken care of by qik into pkj t. So, that is the backward Kolmogorov equation here from 0 then delta t then t plus delta t. So, the first transition will take place to different states during duration delta t, and after that from those states to it will go to state j during interval t. So, that way this is a backward Kolmogorov equation. Similarly, forward Kolmogorov equation, where we have this is 0 then t and t plus delta t. So, that first there will be transition to state k at during time t, and then from those states there will be transition to state j during the incremental time delta t. So, that way we derive the Kolmogorov forward equation, and it is given by Pij dash t is equal to summation Pik t into Qkj over k. Thank you.